Hello everyone. Today we'll be looking at amplitude modulation. So as we know that if the amplitude of a carrier signal is varied in accordance to an instantaneous value of a modulating signal, then it is nothing but amplitude modulated wave. So in this figure, we can see that this is a low frequency signal termed as a modulating signal, and this is a high frequency signal which is represented as carrier signal. Now we can represent modulating signal as Vm equals Vm into sine omega mt, name it as equation 1. Carrier signal Vc is equals to Vc into sine omega ct, name it as equation 2. Now writing the equation for amplitude of an AM voltage, A equals Vc plus Vm, where Vc is the maximum amplitude of a carrier signal and Vm is an instantaneous voltage of a modulating signal. Substituting the value of Vm in this equation, A equals Vc plus Vm sine omega mt. Now we are going to define M as the ratio of both the voltages, that is Vm by Vc. This M is called as depth of modulation or modulation index. Generally, this depth of modulation is expressed as percentage. Therefore, this is also called as percentage of modulation. Here, M takes the value from 0 to 1. We can represent this A is equals to Vc plus M into Vc sine omega mt. That is, we are taking that Vm is equals to M into Vc. Now taking Vc common, Vc into 1 plus M sine omega mt. The voltage of an AM wave V is equals to A into sine omega ct. Representing this A here in this equation, Vc into 1 plus M sine omega mt into sine omega ct. Rearranging the equation, Vc sine omega ct plus Vc M into sine omega ct into sine omega mt. This is in the form of sine A, sine B. So sine A, sine B can be written as half of cos of A minus B minus cos of A plus B. Therefore, Vc into sine omega ct plus M Vc divided by 2 cos of A is nothing but omega c, B is nothing but omega m here. Therefore, cos of omega c minus omega m into t minus cos of omega c plus omega m into t. Now, Vc into sine omega ct plus m into Vc divided by 2 cos of omega c minus omega m into t minus m into Vc divided by 2 cos of omega c plus omega m into t. This is called the final equation for an AM wave. In this final equation, we are able to observe three terms. First term is an carrier signal which is recovered. Then we are having two terms. These two terms are nothing but the side bands. So this omega c minus omega m is called as an lower side band, and omega c plus omega m is termed as an upper side band. Now we'll be looking through the frequency spectrum of an AM wave. We know that in an amplitude modulated wave, it consists of three sets of signals. One is the carrier signal, which does not consist of any information, and there are two side bands, and these side bands are called as upper side band and lower side bands, which are symmetrical, and they are placed at a frequency of Fc plus Fm and Fc minus Fm. So now we can calculate the bandwidth of an amplitude modulated wave as USB, that is upper side band minus lower side band, that is Fc plus Fm minus of Fc plus Fm, wherein the signal which does not consist of any information, carrier signal, will get cancelled, and the bandwidth is equal to twice the modulating signal frequency. If there are n number of sine waves which are involved in modulation, then the bandwidth occupied by this AM wave is given by twice the highest modulating signal frequency. Now we'll see this amplitude modulated wave. In this figure, we can see that this is an modulating signal, and we have a carrier signal, that is a high frequency signal, which is varied in accordance to this modulating signal. and this is called as an envelope, and it is being given by A, which is equal to Vc plus Vm sine omega mt, and similarly we have an exact replica of this, that is minus A, which is equal to minus of Vc plus Vm into sine omega mt. Now we can rewrite this. We know that the modulation index is nothing but the ratio of Vm by Vc. So we also know that modulation index is nothing but depth of modulation, or the percentage of how much modulation will takes place. Generally this will be in the range of 0 to 1. It can never exceed greater than 1, which means that it will be greater than 100%. Now we can rewrite this Vm as, that is Vm is equal to Vmax minus V minimum divided by 2. That is Vm is equal to Vmax minus V minimum divided by 2. Name this one as equation 1. And we can also write Vc, that is Vc is equal to Vmax minus Vm. That is, this is the amplitude of Vc. Vc is equals to Vmax minus Vm. Substituting for Vm, we can rewrite this as Vmax minus of Vmax minus V minimum divided by 2. Solving this, we'll be getting Vmax plus V minimum divided by 2. That is Vc is equals to Vmax plus V minimum divided by 2. Name this one as equation 2. Now that is M is equals to Vm by Vc, which is equal to Vmax minus V minimum divided by 2 divided by Vmax plus V minimum divided by 2, which reduces to Vmax minus V minimum divided by Vmax plus V minimum. Now we'll be looking through the power relations in an amplitude modulated wave. The total power Pt in a modulated wave can be written as V square of a carrier signal divided by R plus V square LSB divided by R plus V square USB divided by R, which means that the total power is expressed as the power of a carrier signal, power of a lower sideband signal, as well as the power of an upper sideband signal, wherein all these three voltages are RMS value, and R is nothing but the resistance of an antenna. The first term is nothing but an unmodulated carrier, that is Pc is given by V square carrier divided by R, which can be expressed as Vc divided by root 2 whole square divided by R, which is equals to Vc square divided by 2R. Similarly, power of an lower sideband is equal to power of an upper sideband, because we know that both the sidebands are symmetrical. So which can be given as V square SB divided by R, which is equals to M into Vc divided by 2 divided by root 2 whole square divided by R. What is this M? M is nothing but depth of modulation, which in turn gives as M square Vc square divided by 8R. Okay, so that is equal to M square divided by 4 Vc square divided by 2R. Name this one as equation 1, this as equation 2. Now substituting these equations in Pt, we get Pt is equal to, so what is this? V square carrier divided by R is given as Vc square divided by 2R. Then this, that is power of an lower side band, is being given as M square divided by 4 Vc square divided by 2R. Then power of an upper side band is given by M square divided by 4 Vc square divided by 2R. Now we can take Vc square divided by 2R as common. 1 plus M square divided by 4 plus M square divided by 4, which is equal to, what is this Vc square divided by 2R? Vc square divided by 2R is nothing but Pc into 1 plus 2 times M square divided by 4, which is equal to Pc into 1 plus M square divided by 2. That is Pt is equal to Pc into 1 plus M square divided by 2, or Pt by Pc is equals to 1 plus M square divided by 2. That is when when M is equals to 1, there will be an maximum power in an amplitude signal wave, that is Pt is equals to 1.5 Pc. Thank you.